Okay. All right, so in general, what we just defined in terms of work, we have a more generalized name for, which we call the line integral of a vector field. And so if you imagine that we have this vector field here, we're just calling the I component P, the J component Q, and the K component R, then we can define the line integral to be, so let's start with this top line here. I'm going to call this my shorthand representation, which is not how we actually evaluate. And then down here, we'll show you how you actually evaluate. So we're going to start by what we just showed on the previous page. We did this in the context of thinking of it as work. My shorthand representation is f dot t ds. I can't actually evaluate like that. I have to change variables. And so when I parameterize and do everything in terms of t, this is going to become f. And here you can assume f is going to be of a function of t. I'm not going to write all that piece out here just to keep it short. F dotted with b dt. That's what we showed on the previous page, where both f is now written in terms of t based on your parameterization, and v is coming from your parameterization. So that's shown down here. Okay, now I'm going to show you two other ways we represent this. And again, these are all mean the same thing. It's just shorthand. So notice down here, another way we can think of this is v is really dr dt, right? So let's plug that in for v. Instead of writing it as velocity, we're going to say, well, that's the derivative of my position and then dt. That's going to lead us to another shorthand notation we'll put up above, which is saying a nice way to think of this is just as f dotted with dr. Okay, because really what we did down below was we noticed dr dt times dt here. My shorthand would just be to call this f dot dr. This does not mean anything. I can't do anything with it until I change variables and do it this way. So this is just mathematical shorthand. These are equivalent. The other way you can think of this as being equivalent is that we think of this TDS ends up being equivalent to DR. Okay, now we have one more way that we write this out in actual evaluation. Like let's say we're going to start to do this dot product. And so we need to take this vector f, which is here, and then take my dr dt. And as a recollection, or just recall, dr dt is going to be the derivative. It'll be dx dt, dy dt, dz dt. So let's say we start taking the dot product, the I components. I'm going to have p times dx dt. And I'm writing p right now. I know up here it's a function of x, y, and z. When you actually evaluate, you're going to have to plug in what x, y, and z are in terms of your parameterization, so that p at the end of the day will become just a function of t. Just to save space, I'm not writing all that down here, but anything in this green region, because we're integrating with respect to t, we are assuming you've converted these things to all be in terms of t. Okay. All right, so we're going to keep going. Then I'm going to take the the next thing is multiplying the j components, which is going to be q dy dt, and then r dz dt. And I'm integrating all of that with respect to t. So this is going to lead us to our third shorthand representation, which is going to say, well, what if we just wrote this as p dx plus q dy plus r dz. And again, just like we did with the middle representation, this is meaningless until you change variables and basically divide by dt, multiply by dt here, and write it in something that we can actually calculate it. Same thing here. This is meaningless. I can't just integrate with respect to x, y, and z here. I'm going to convert everything to be in terms of t and then integrate. So this is just shorthand that you'll see, and I wanted you to see all three because we will use them interchangeably. We'll actually use all six interchangeably, so you might see it in the form where we're actually evaluating it. You might see it in these shorthand forms. They all mean the same thing in terms of the math that you're doing. Now, in terms of the physical application, we already talked about work, but there's actually a couple other physical interpretations we can take out of this, depending on what your vector field F represents. So let's summarize. Oh, and what I want you to think about also is, because I'm taking the dot product between F and a unit vector, unit tangent vector T, that's really a projection then. If you recall, the dot product, when I'm taking dot product with just a unit vector, it gives me the scalar component of the projection here of F onto T, because this amount right here is just going to be magnitude of F times cosine theta, but that ends up being F dotted with T since T is a unit vector. So really what we're getting is a scalar component of a projection, which means when we add that up everywhere over my line or my curve, this is measuring the extent to which F is going in the direction of C. And we can interpret that if F is a force field, then this quantity, which we showed on the previous page, is going to give us the work. If F is a velocity field, then we have a different name. We call this quantity the flow of F along C. And in particular, if it's a closed curve, and by closed, we're just meaning that my curve here is connected this way, then this quantity is going to be giving us what we call the circulation. So if it's a closed field and we're looking at F as a velocity vector field, then this is going to be giving us what we call the circulation, and we denote that by putting a little circle on the integral sign to let us know we're integrating over a closed curve. All right, so we're going to move on. Let's try this example. I want you to take a moment, put it on pause. This is helping us just to think geometrically how we can interpret this line integral of a vector field. So I have this vector field E here, and I have 4 different curves, and I would like to know which of the line integrals are positive and which are negative, and then arrange them in ascending order. So go ahead, put it on pause and see what you can do. Okay, first thing you can notice is all of these should be positive except for the line integral over C4, because in this case, you can see this vector field E is moving in the opposite direction as C4. And because really what I'm doing is taking the dot product between the blue vectors here and a tangent vector to the black curve. So tangent vector going here would be a little tangent vector. Here's another one. Here's another one. We know when we take the dot product between two vectors that are pointing in opposite directions, we'll have a negative value because the cosine or the angle between them will be negative. So all of them are going to be positive except for E.dr. And so if we're listing them in ascending order, that helps us realize that this will be the smallest. And let's see what the next smallest would be. Let's do all of these, get them ready. Okay, so next, I want you to think about, this is really helping us think about dot products, because as a recollection, E.dr, as a reminder, is the same as the dot product between E and the unit tangent vector. So we're just going to picture what's happening with the dot product between E and the unit tangent vector along different curves. Let's look along C1 versus C3 next. Okay, so they told us both C1 and C3 are the same length. So that's important. But now, and if I look at this blue vector here and imagine the dot product of a blue vector along this curve, right? So I'm going to slide this blue vector in my head down towards this black curve because I'm going to assume the vector field at the actual black curve is pretty much the same. Okay, so taking the dot product between these two, they're basically pointing in the same direction. And so the cosine, I'd assume the angle between them is pretty much like 0. And so what's going to be contributing to the integrand is the magnitude of E. And here that magnitude is long. So I would expect the integral of the dot product over this curve to be bigger than the one over this curve. Even though C1 and C3 are the same length, it's because the magnitude of E is smaller along this curve than it is here. And so when I take the dot product along this curve, I expect a larger contribution from the field. Okay, now we also need to compare, before I put those in C2, where we think C2 goes in this. So it appears to me that C3 and C2 are kind of along the same trajectory. So I would expect the angle between this blue vector and my tangent vector here to be pretty much 0 also for C2. And it looks like the length of the magnitude of my blue vectors are the same on C3 and C2. So I would expect this and this to be roughly the same for C3 and C2. The only difference is that C2 is longer. And so when I'm integrating, I'm adding up over this curve, and that's going to end up giving me a larger number because I'm adding up that quantity over a longer curve than here. So using that reasoning, I would expect that C2, this line integral over C2 is going to give me the largest quantity, and then the next largest would be over C3, and then after that, C1 would be the next largest, and then we know over C4 will be negative.